Welcome to Cloud Wizard. In this video, we are doing a complete deep dive into the load balancer, the reverse proxy that sits in front of your backend servers and decides where every request goes. We will cover Layer 4 versus Layer 7 balancing, round-robin, least connections, consistent hashing, health checks, sticky sessions, SSL termination, and the low-level design needed for a senior system design interview. Whether you are preparing for a FAANG interview or building infrastructure that scales, this one is for you. Let us get into it. Welcome to Cloud Wizard. In this video, we are doing a complete deep dive into the load balancer, the unsung hero of every large-scale distributed system. If you have ever wondered how platforms like Amazon, Netflix, or Google handle millions of requests per second without a single server melting down, the answer starts here. We will cover what a load balancer actually is, the difference between Layer 4 and Layer 7 balancing, the most important load balancing algorithms, health checks, session persistence, SSL termination, and how to design one in a senior system design interview. Whether you are preparing for a FAANG interview or building backend infrastructure, this one is for you. Let's get into it. Here is the core problem. A single application server can only handle so many concurrent connections, so much CPU work, and so much memory. When traffic grows, that one server becomes a bottleneck and a single point of failure. A traffic spike can overwhelm it, causing timeouts, errors, and a bad user experience. Even if you add more servers, clients still need a single place to send requests, and someone has to decide which server handles which request. Without that decision maker, traffic lands unevenly. Some servers sit idle while others overload, and a failed server keeps receiving traffic because nobody notices it is down. The load balancer solves all of this by sitting in front of the backend pool, distributing requests intelligently, removing unhealthy servers, and enabling horizontal scale. Let's walk through the functional requirements. First, the load balancer must accept incoming client connections and distribute them across a pool of backend servers using a configurable algorithm. Second, it must run health checks to detect unhealthy or overloaded backends and stop sending traffic to them until they recover. Third, it should support session persistence, also called sticky sessions, so that a user's requests consistently land on the same backend when the application stores local state. Fourth, it should handle SSL termination, decrypting HTTPS traffic at the edge so backends can run plain HTTP and focus on business logic. Fifth, it must support dynamic backend registration and removal, allowing DevOps teams to scale out, deploy new versions, or drain connections without downtime. These 5 capabilities make a load balancer production ready. Now the non-functional requirements. The load balancer must add minimal latency, because every request passes through it. It must sustain high throughput, potentially millions of requests per second, without becoming the bottleneck itself. It must be fault-tolerant, surviving backend failures, partial outages, and even failures of load balancer instances through clustering or redundancy. It must be secure, offering DDoS protection, access control, SSL handling, and sometimes web application firewall features. It must be observable, emitting metrics on latency, throughput, error rates, and backend health. And it must be operationally simple to reconfigure, scale, and upgrade without dropping active connections. Here is the high-level system architecture. On the left, clients make requests that are resolved by DNS, possibly with a global server load balancing layer that picks the closest data center. Inside the data center, one or more load balancer instances sit behind a virtual IP or anycast address. The load balancer has a listener that accepts incoming TCP or HTTP connections, a routing engine that chooses a backend according to the configured algorithm, and a health checker that continuously probes the backend pool. An SSL terminator decrypts HTTPS traffic. The load balancer forwards requests to a pool of backend application servers, which may read from a database, cache, or object store. Metrics and logs are emitted to an observability backend, and a control plane manages the configuration, backends, and weights. The key metrics to memorize cold. Throughput, measured in requests per second or connections per second, tells you how much traffic the system is handling. Latency, especially P50 and P99, tells you whether the load balancer is adding overhead and whether backends are slow. Error rate, including HTTP 5XX and health check failures, tells you when backends are failing. Active connections per backend show whether traffic is evenly distributed. Backend utilization, such as CPU and memory, helps with capacity planning. An SSL handshake time measures the cost of TLS termination at the edge. These are the metrics you should monitor, alert on, and optimize in a real interview or production system. Let's trace the end-to-end user journey. A user opens a mobile app and sends a request to a website. DNS resolves the domain to the load balancer's virtual IP. The load balancer receives the request, checks which backends are healthy, applies the configured algorithm, and forwards the request to one of the backend servers. Because the user has a shopping cart stored in local session, the load balancer uses a sticky session cookie, so the user's next requests go back to the same server. Later, one backend starts failing health checks. The load balancer removes it from the pool within seconds, the user's next request is routed to a healthy server, and the mobile app keeps working. Meanwhile, the platform team adds 2 new backend instances to handle a sale event, and the load balancer automatically starts sending traffic to them. The core models and algorithms. Round-robin assigns requests to each backend in cyclic order. It is simple and fair when all requests are similar. Least connections routes to the backend with the fewest active connections, which works better when requests have different durations. Weighted variants of both let you send more traffic to larger instances. IP hashing or consistent hashing maps a client to the same backend based on source IP or a key, which helps with caching and session locality. Health probes are active checks like HTTP ping or TCP connect, and passive checks that watch actual response errors. Sticky sessions maintain affinity via cookies, source IP, or application-level session identifiers. SSL termination offloads TLS decryption to the load balancer. The key trade-off is between simplicity and optimality. The best algorithm depends on request size, backend capacity, and whether you need stateful sessions. Now the low-level design deep dive. The load balancer maintains a backend pool data structure with entries for host, port, weight, region, and current status. A connection counter tracks active connections per backend. A health registry records the last known state of each backend and the timestamp of the last probe. A routing table maps host names or path prefixes to specific algorithms and backend pools. A session table maps session identifiers to backend identifiers when sticky sessions are enabled. On every request, the listener parses the transport or application headers, runs the health filter to exclude down backends, applies the selected algorithm, optionally applies session affinity, forwards the request, and updates counters and metrics. Health checks run on a separate scheduler with retries and configurable timeouts. The control plane pushes configuration changes and the load balancer cluster elects a leader or uses a distributed state store to keep consistent backend lists. Key takeaways for your interview. First, a load balancer is a reverse proxy and traffic distributor that enables horizontal scale and removes single points of failure. Second, choose the right algorithm. Round robin for uniform work, least connections for variable work, and consistent hashing for session locality. Third, health checks are non-negotiable. Without them, failed backends continue to receive traffic and cause real user errors. Fourth, understand the difference between Layer 4 load balancing, which routes based on TCP or UDP, and Layer 7 load balancing, which can inspect HTTP headers, cookies, and paths. Fifth, SSL termination and session persistence are common edge responsibilities that affect security, latency, and state management. If you can explain these 5 points with a clean architecture, you will signal strong senior-level design thinking. That's it for the load balancer. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that is a wrap on the load balancer. We covered the full picture, from traffic distribution and health checks, through algorithms, session persistence, SSL termination, and the low-level design of the backend pool and request flow. If this video helped you, Please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.